All right, no questions in advance. Again, these are office hours. They're open to anyone. These are not lectures, so make sure that you're not relying on these as a substitute for lecture. There's already videos about that on the course website. So if you got questions, ask them in the chat. I'll give you about 5 minutes. Otherwise, I'm just going to kind of mess around online, pick up the banjo, do a little practice today. But this is your time. We are coming up on a long weekend. So July 4th, holiday weekend. This means Monday the school is closed. There are no live streams Monday. So if you're looking for that link, you're going to see that the announcement this week. There is no link because we are off Monday because it's a federal holiday. But since the federal holiday fell on the weekend, we get to take it the following Monday. Now, a few comments on there are 2 discussion boards next week. One is calculating the delta G for a reaction as well as the correction factor, assuming your non-equilibrium conditions. That's relevant to the upcoming test. There is one following it about titration and Henderson-Hasselbalch equation that is not relevant to the exam. So if you look at the discussion board for next week that's due on Thursday and you're like, this really isn't the notes, it's because it's kind of a jump start on the acid base. Ideally, you would take the exam next Wednesday or Thursday, but I want to give you the whole weekend to take it. So feel very much free to put like 4 attendance for that discussion board Thursday. It's actually a pretty easy problem once you get access to the notes, which you'll get access to them Friday morning. So that's about it for commentaries. Yep, I'm here if you got questions. Good morning, Dia. How are you? Number 4, test 3, homework, journal thermo. All right, let me bring up the homework. Got a feeling I know which one this is too. So the entropy on that one you can't really tell. So okay, let me see if this is the same one. Test 4. 4 and test 3, homework. I'm doing well this morning. Journal thermo. So carbon monoxide gas plus H2O liquid, or H2O gas, goes back and forward to H2 gas and CO2, and this is what's called the water gas shift reaction, or WGS. So in terms of the delta S here, we don't see any phase changes. So we have 2 moles of gas on the left, 2 moles of gas on the right. So we're not really gaining entropy from a phase change. We're not gaining entropy from breaking apart molecules. So we would say here the change in delta S is about 0. And this ends up being true. I think the change here is like 2.7 joules per mole Kelvin. Like it's a very trivial, small amount of entropy change. So for this particular one, wait, did I put it in there? Yes, it is. There you are. So for this particular reaction, I would say like your delta G, your delta S is small, if not zero at all. And again, the reason being is you're not really seeing any phase changes. If we had like 3 moles of gas here, or 4 moles here and 2 here, we'd say the delta S is negative. If we saw this going from like H2O liquid to 2 gases, so 1 gas to 2 gas, we'd see like the delta S is greater than 0. But if you're not really seeing phase changes, you're not seeing a change in the number of molecules, your delta S here is pretty negligible. And this is actually kind of an issue with this reaction. Because the delta S is 0, it's purely driven by enthalpy changes alone. At low temperatures, you favor the formation of water over the formation of H2. And so for the water gas shift reaction, it's really hard to get high yields of H2 gas, which is what you want, because at low temperatures, actually the reverse reaction, CO and H2O, is much more favorable. Yeah, well, we're looking at delta S changes. We're going to do qualitative in this course. We're not going to do anything quantitative. There's no point in doing anything quantitative with the delta S. Mostly so you get a feel for when you expect entropy changes to increase and decrease. But you're very welcome. Christian, can you explain the general idea of microstates and how all that connects? I was slightly confused while reading the textbook. Um, so let's say we have a 9 by 9 grid. Hopefully I can manage this. And in this 9x9 grid, I have the restriction that I have to have 3 tiles that are colored in, and those 3 tiles have to be touching each other in kind of this L shape. It's a little bit off screen. And so macroscopically, the only requirement here is that when I get done, there's always this L-shaped 3 squares. Actually, let's do 4. There's this square-shaped, there are 4 boxes that are colored in. So how many different ways can I do that on a 9x9 grid? Well, there's 1, 2, 3, 4. So there's 4 ways I can arrange this that I can end up getting 4 squares colored in that way. And so in this case, the number of microstates here is 4 because we meet the requirements that overall we always have the 4 blocks touching. Now let's say I go back to the one I was planning on doing, which has just the 3. So the 4 here is this shape, and we look at the number of microstates for the L shape. If we can put the restriction on here that the L shape has to have the bottom right one open. Well, we've got 1, 2, 3, 4, and I would say that's it. We also get 4 microstates. So now let's put the restriction on it that we can rotate it. So we got 4 microstates if we've got that, but then we'll say that this can rotate as well. So if this can rotate, I had the original 4, but then I can also add a couple more, or 4 more. So I can rotate it 90 degrees, and I still meet this constraint. So the idea of microstates is that macroscopically we should meet this constraint. In most cases, this constraint is temperature, pressure, and volume. But individually, if we look at the microscopic scale, there's lots of different ways we can arrange these and get the same global average we were expecting to get. So in the case of 4 colored in squares, there's 4 combinations. The combination of 3 in the L shape, there's 4. If we allow rotation, we end up getting more and more permutations. And so omega here, the number of microstates, is going to be greater than 4. Now, you can kind of see here when we start taking restraints off of it, it begins to get easier and easier. So if we look at just having 1 colored in square, there's 9 different possibilities. If we have 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so forth. So how we define the macroscopic view will determine how many different microstates we can get, but the number of microstates here is going to give you a feel for how many, basically the entropy, the number of, the restrictions you have on how you have to arrange it. So yeah, I'm like trying to think of this example on the fly. So this is the idea of microstates. How many different ways can you arrange a microscopic system and still get the appearance you expect at the macroscopic state? So macroscopically, for the same pressure, volume, and temperature, how many different ways can you arrange it microscopically? And this is what gives rise to entropy. And this is why systems like to progress towards higher entropy, is that it provides a variety of options. It's not disorder, because you can see in this example that's actually very ordered. I put some very high restraints here on what's allowed to happen, but just by allowing a little bit of rotation, the shape hasn't changed, but allowing it to rotate a little bit, I've created more options, and therefore I've increased the entropy. Now the thing is that this is all based on statistical analysis. There's a great history behind this, behind Ludwig von Boltzmann, who created this field because he actually hated a lot of people, and like this is one of those like big flex on moments where he created the field because he hated people and created this whole field of statistical mechanics just to spite them, and then in the end like hung himself because he was really upset it ended up being right. He didn't like the idea of the universe being probabilistic. But the point I'm trying to build to is that microscopically we could observe any of these configurations. We just don't know which one. So if you were to sample thousands and thousands of, let's say you had gas in a tank, and you were to look at thousands of tanks that were exactly the same, you could find there's an equal probability that all of these would be observed. The thing is that we don't know what each individual tank looks like. We don't know at a given point in time and space which microstate is actually there. We just know that all of these are possible, and we can definitely put things where like there's a restriction on it. Like let's say for some odd reason, this right corner penalizes the squares being closer. And we can calculate, we can set that penalty to be a quantitative penalty. We would still expect to see all the different configurations, but we expect it to lean more heavily towards a certain microstate because that microstate's lower in energy. That just means that we're less likely to observe the others. So this is a also kind of the confusing thing about microstates is like all of them are possible, and we can have a higher or lower likelihood of seeing them. But these microstates here all look the exact same in terms of energy. They look the same in terms of pressure, volume, and temperature. So we're equally. It's not impossible to rule out seeing any of these given microstates if we looked at it microscopically. But because this is based on statistical mechanics, we don't know which one we're going to see individually. So we just say it acts like these are all present. Yeah, I hope that didn't confuse you more. You're welcome. I generally find thermo is really terribly explained. I have like 4 thermo books and only one does a good job of it. So if you feel really confused by thermodynamics, like welcome to the club. I took it at state and undergrad, and honestly, I think it had a negative impact on my understanding of thermodynamics. It wasn't until grad school did I have one really good instructor who explained it very well. We actually had a very good textbook that explained it. It is a graduate textbook, and it presupposes you know a lot of this information, which why I don't use it at the undergraduate level is like it does make some assumptions about your abilities. Generally, I lump it in there with physics in terms of things that are really not that complicated. They're just generally very poorly explained. And that definitely kind of sums up my undergraduate experience with thermo. I think it's, from a big picture standpoint, it's very easy to understand what's going on with thermo. The devil is really in the details, and that's what makes it complicated. But oddly, the people that understand thermo like to teach it from the details, and it just makes it super complicated to understand. Like I don't. It's like teaching chemistry from like quantum mechanics up. Like I get that we do that as Wake Tech. That's really hypocritical, but I don't think that's a good way to understand it because if you understand quantum mechanics, you don't need general chemistry. You've already taken general chemistry. Now I agree, quantum mechanics can really help you understand macroscopically what's going on. I don't think it's a good starting point for understanding it. It's like people that try to explain calculus using calculus is like that doesn't really do somebody who doesn't know calculus a lot of good. Understanding microscopic microstates, microcanonical ensembles, macrocanonical ensembles, like there's a whole list of them. If you already understand that, you probably don't need an intro to thermo course. Now, I will grant you it makes an intro thermo course much easier to understand if you do that, assuming you already know it. But yeah, I took it at state and undergrad, and I really unlearned nothing. I really had to go to grad school to understand thermo. It was like learning that Gibbs free energy is just the sum of all the entropy contributions. Like, well, that makes a lot more sense than what people were telling me. Because they were trying to tell me, it's like, well, it's useful work, it's this. It's like, that doesn't make sense when you say, well, it's just the sum of all the energies. It's like, oh, that's why the Gibbs equation is the way it is. Cool, that makes a ton of sense. And then you can see how you would interpret it as useful work. Because that was the other thing as I got into electrochemistry for my thesis work, and um, so you'll see people post in the discussion boards about how delta S is the wasted heat, and I said in a previous video like that's only true if you're working with a heat cycle. But because so many people work with heat cycles, they try to like retroactively apply that to the definition of entropy, and it creates this weird misconception that that's the only thing entropy is waste heat. Entropy can take a lot of different forms. I really would love to see a well-written undergraduate textbook in thermodynamics. I don't think we're ever going to get one. And it doesn't surprise me because my experience with physics in college. So, I took physics in college, physics 1, physics 2, and electricity and magnetism was the state functions. Okay, state functions are actually not that bad to understand. So, easiest example of a state function. Let's say we have a map, and it's a map of Wake County. So we've got Raleigh, and we've got Northern Wake Campus. Sorry, Scott Northern Wake Campus, and Southern Wake Campus. And there are two questions here. What's the distance? What's the time between the two campuses? So the distance never changes. And that's because the distance is set by longitude and latitude, which are fixed points on a globe. So we would say here that the distance between the two is a fixed state, meaning that it's uniquely defined. If you have latitude and longitude, you have a uniquely defined point, and that point doesn't depend on where you came from. It doesn't matter how you got there. It is what it is. So equivalent for thermodynamics, we have pressure, temperature, and what's called molar volume, which is just volume divided by moles. And this uniquely defines the Gibbs energy, the enthalpy, the internal energy, the entropy, all those other quantities. So for a fixed state, it doesn't matter where you came from, it doesn't matter where you're going to, the only thing that matters is where you are. If we consider time though, time does depend on a lot of things. So if you go at 5 p.m. versus 1 a.m., your time between campuses is going to be radically different. And the reason is because of traffic. Traffic acts like a dissipative force. The more traffic it is, the longer it takes to get you there. So in this case, time is not a fixed variable. The time between the campuses fluctuates depending on what's going on. So if we are working with a non-fixed variable, the quantity that we're measuring will depend on the pathway we take. So if you go from Southern Wake Campus to Northern Wake Campus using, let's say you go up 401, it'll get you there. That's going to take a different time than if you skirt around and use 440, or if you slip up the 540 transfer. These are, even though you're going between the same two campuses, you're going to the exact same place, the route you take is going to have a major impact on what's happening. So when we say a fixed state, it basically means that it's uniquely defined only by certain parameters. In thermodynamics, temperature, pressure, molar volume. Does not matter the history. And this is really powerful for us because if we know the heat of formation of, let's say, calcium oxide at room temperature and atmospheric pressure, that's it. We don't have to worry about how we made the calcium oxide. We don't care if we took the calcium and oxygen and really mixed them, or this calcium oxide was formed by calcium carbonate decomposition. It's calcium oxide. The fact that it's at room temperature and atmospheric pressure means that it's enthalpy, it's entropy, it's Gibbs energy, it's Helmholtz energy. All thermodynamic parameters are the same no matter how we made it. But if it wasn't a fixed parameter, it would matter. So it may take more energy to make calcium oxide from calcium carbonate than it does from like calcium and oxygen, which just spontaneously react. So that's the difference between a fixed state and a non-fixed state. The big implication for this is thermodynamics. For non-fixed systems, these are what are non-fixed states. These are called dissipative systems. This is where the entropy of the universe is always increasing comes from. That even though the Gibbs, the enthalpy, the entropy, the internal energy, all that is fixed between the two, because there is an activation barrier between the two. So we talked about this with reaction kinetics. So let's say you go from calcium and oxygen to calcium oxide, CaO. This part here is fixed. But the thing is that we need only this much energy to get over the barrier, but there's definitely molecules that have more than that. So anything that has more than that just kind of overshoots, and this is where your delta S of the universe getting bigger comes from, is that a lot of things have excess energy to get over that. Yeah, you're welcome. A lot of things have excess energy to get over this barrier, and so we think about this as friction. It's kinetic friction, as in reaction kinetics. And that kinetic friction is why the delta S of the universe is getting bigger and bigger and bigger, is that if you got more energy than you need, it's wasted energy. That said, this is also where the trade-off between speed and efficiency come from. Generally, the faster the reaction, the more energy you threw at it to get over the barrier, but all that extra energy, even though it got it over the barrier faster, meant that you lost it to the environment. This is a trade-off because we talk about plants being really efficient at photosynthesis, and this is true. They are super efficient. They're also very slow. And nature likes going to high efficiency systems because it reduces waste energy. It's more practical for a plant to use as little energy as possible. But photosynthesis is super slow, and because it's super slow, it's not really practical for like powering your house. Now you can go to solar cells. Those produce a lot more electricity, but the trade-off is like they're not going to get the efficiency of like a plant. So in our fixed versus non-fixed example, the delta G of the reaction, difference between products and reactants, that's fixed. The EA, not fixed. And this is a design consideration. If you ever go into like reaction engineering, like you really worry about that. So it doesn't look like there's really anyone left here. Again, these are office hours. You're free to use them as you need them. So I will see y'all Tuesday. Again, keep in mind that Monday's a holiday for us because we don't get July 4th Saturday. We don't get that off, so we get Monday off instead. All right, I will see y'all next week.